This lesson is part 1 of section 9.5. We're going to be talking about inverse trig functions today. So we're going to give you an introduction into inverse trig functions, and specifically we're going to look at the graphs of trig functions in order to define their inverse trig functions. And then we're also going to evaluate inverse trig functions and also compositions of trig functions. Alright, we're going to begin by looking at the graph of a sine graph. So here is just the graph of y equals sine of x. Now recall that a function has to be one-to-one in order to have an inverse function. So what does this mean? Well, we studied this way back in the beginning of the first semester, and we know that a function is one-to-one if it passes the horizontal line test. So clearly the sine function here fails because it's going to intersect the graph. This horizontal line will intersect that graph at multiple points, which means that it fails that horizontal line test, which means it does not have an inverse function. However, we're calling this the inverse sine section, so we must have an inverse sine function here. So what happens is we actually restrict our sine function to just the interval between negative pi over 2 here to pi over 2. Okay, so we basically pretend like the rest of the graph isn't there, and now if we just look at what's between those values here, now it is a one-to-one function. Now it does pass that horizontal line test. So the domain here of your sine function is now going to be restricted, like I said, to negative pi over 2 to pi over 2, and your range then is still negative 1 to 1. Okay, so that corresponds on the unit circle here to this shaded portion here in red. Okay, so keep that in mind. So now that we've restricted that domain of our sine function, we have a unique inverse function that's created. We call that the inverse sine function. Okay, so I'm right here now. Now we denote that inverse sine function two different ways. So we've seen it written as y equals the inverse sine of x, which is basically consistent with your inverse function notation, right? F inverse x. And again, remember that this is not equivalent to 1 over the sine of x. So make sure you don't want to, confuse that in your head. We also can denote that as y equals the arc sine of x. So this notation, the arc sine of x, actually comes from the association that we make with the central angle and the intercepted arc on the unit circle. So really arc sine of x means the angle or arc whose sine is x. So the angular arc measure whose sine is x. So basically we will see either of those interchangeably throughout this section. Okay, so now I want to graph our inverse sine function, this arc sine of x. Now in order to graph that inverse sine function, all we need to do is take a look at our sine function and where we restricted our domain. So I'm going to come up here and I'm just going to look at the coordinates of this graph, because remember, when you graph f of x, you take a coordinate xy. On the graph of its inverse, f inverse x, we would have the coordinate yx. So all that happens is that those values switch. So here I've got the coordinate pi over 2, 1, and down here I have the coordinate negative pi over 2, negative 1, and obviously the coordinate 0, 0. So on my inverse function down here, I still have that coordinate 0, 0, switching that doesn't really change anything. But then I have the coordinate 1, pi over 2. Okay, so there's my coordinate 1, pi over 2. So let's just show those values here. I also have the coordinate negative 1, negative pi over 2. Alright, so after I create those coordinates, I'm just going to draw a smooth curve that connects them. Okay, so that's the graph of your inverse sine function, the arc sine of x. So these are the same thing, right? Just different notation. So really what this is a reflection over that line y equals x of your sine curve, where it's restricted between your values of, negative pi over 2 to pi over 2. So let me try to graph this nicely for you. Okay, so in blue here you can see I try my best here to show that this is the sine of x. This is slightly curved right there. I'm just trying to show that sine curve from the value of negative pi over 2 to pi over 2. Right, so we're at negative pi over 2, negative 1, and pi over 2, 1. And then that coordinate right here in the middle at 0, 0. So I'm just, it's not that great, but you get the point hopefully. So you see that it's actually a mirror reflection right over the line y equals x. So there's your inverse sine function and your sine function graphed on the same graph. All right, now that we know what the general shape of that inverse sine function is, I want to use that and our just basic knowledge of inverse functions in order to find the domain and the range of our inverse sine function. So in order to do that, we're just going to use our basic knowledge of inverse functions. We've studied before that the domain of our function becomes the range of our inverse function and vice versa. So before we had a domain for our sine function of negative pi over 2 to pi over 2. Well, that becomes our range here. Negative pi over 2 to pi over 2. Oh, you know what? I should do this in red since the graph of the sine is in red. And you can clearly see your range here goes from negative pi over 2 to pi over 2. And previously, the range of our sine function, right, it only oscillates between negative 1 and 1, so values of negative 1 to 1. Well, that becomes now the domain of our inverse function. So it goes from negative 1 to 1. All right, so I panned out now so that we can get a big picture of the entire idea here. Now, the reason why we are looking at the domain and the range of our inverse sine function is because when we try to evaluate inverse, trig functions, in particular here, we're starting off with inverse sine. So we have the inverse sine of 1/2. Well, first, in order to evaluate this input here must fall within the domain negative 1 to 1. Since it does, we would have a value. Now, the only possible value from this inverse trig function here is going to come from the interval negative pi over 2 to pi over 2. So this is where all of those solutions would lie. Okay, so any output has to fall within your range, negative pi over 2 to pi over 2. So this is all of your possible answers. This is the location of the possible answers to your, these questions here where it asks you to evaluate the following inverse trig functions. So let's actually calculate here and evaluate the inverse sine of 1/2. Now, there are two possible places where the sine is 1/2 on a unit circle. Right? This is what that question is actually asking. What is the arc measure or angle measure where you end up with the sine of 1/2? So you've got two possibilities. One at pi over 6 over here. Remember, this is the short value. So one at pi over 6 and one over here at 5 pi over 6. But 5 pi over 6 does not fall within your interval negative pi over 2 to pi over 2. Remember, your possible solutions here come from this part of the unit circle. Okay, so we're only going to select then pi over 6. So notice that I have a ratio here. My answer is an angle measure. Okay, that's very important that you understand. You're looking for an angle measure here, not a ratio. So let's try the next one, arc sine of negative 1/2. So again, this question is asking, what is the arc or angle measure that will give you a sine of negative 1/2? Now that occurs in two spots, again, just like the previous question, on your unit circle. Now this is the low point, right, for the sine, so this is closest to the x-axis. So we've got 2 points where we have a negative value for sine, and they're both in the pi over 6 family. Now this one is 11 pi over 6, because it's just shy of 2 pi, and this one here is just greater than pi, sorry, so that would make that 7/6 pi. Okay, now neither of these values, though, fall within our range. Remember, you want to restrict your values between negative pi over 2 to pi over 2 here. So this is definitely the point that we want, but it's not in the form that we need. So we're going to look for a coterminal angle. Now, coterminal angle is again a term that we want to review. It just means that it has the same terminal side. So this angle, 11 pi over 6, that means you're going all the way around here, and you end up with this angle measure here. Well, that's the same as this angle here, right, which is negative pi over 6. Now, negative pi over 6 is within our domain of, our range of negative pi over 2 to pi over 2. So the arc sine of negative 1/2 is negative pi over 6. So even though 11 pi over 6 gives you that value here, you have to make sure you're selecting values, theta values, that are between negative pi over 2 and pi over 2. All right, next up we want to evaluate the inverse sine of negative 2. Now, there are two ways that you can approach this problem. One, right away you can recognize that this value, negative 2, does not fall within the domain of your inverse sine function. Remember, its domain is from negative 1 to 1. So right away you should say to this, okay, there's absolutely no way you can even input this into your sine function, which means there is no value. It's not necessarily no solution because we're just asked to evaluate, but there is no number here that will satisfy this. Now, a second way to think about this is, again, you're answering the question, what is the angle measure whose sine value is negative 2? Well, if you think about a sine graph that oscillates between -1 and 1, so that value can never equal -2. So the sine of x, no matter what you input for your angle measure, will never equal -2. So there's, like I said, two ways to approach that same problem. All right, the last three questions here on this part of the note sheet are all composition of functions. So here I have the inverse sine of the sine of pi over 4. Now, when we studied inverse functions, you guys might remember your fundamental identities for inverse functions, and that was something like f inverse of f of x is equal to x, and f of f inverse of x is equal to x. So we studied that quite a while ago, but maybe you remember this. Now, essentially what that says is as long as x is in the domain of f, then when you take the composition of f inverse of f of x, you end up with just x. And likewise, as long as x is in the domain of f inverse, then you can take the composition f of f inverse x and end up with just x. So whatever's inside here, so let's say I had f of f inverse of 3, as long as 3 is in the domain of f inverse, then this is going to just equal 3. It doesn't matter what, you don't have to take any composition at all. You can just assume that that gives you, it maps back, right? It's a one-to-one function, so it should map back. Now, in this case, a shortcut for this problem would be to apply what we were just talking about, but you have to make sure that this here, this input, is within the domain of the particular function you're looking at. So, is pi over 4 within the domain of sine? Yes, it is, which means then this is pi over 4. So that's one way of approaching this question. Okay, now there's a second way to approach this problem, and this is actually the method that I would prefer you to use, but basically you're going to look at the sine of pi over 4 here. So the sine of pi over 4 is root 2 over 2. And then I just need to take the inverse sine of root 2 over 2. Now this is within the domain of the inverse sine. So I end up with pi over 4. Now obviously there are two values on your normal unit circle where you end up with root 2 over 2. One at pi over 4, so positive root 2 over 2, and the other one here over at 3 pi over 4, right? But obviously that's not within your range, negative pi over 2 to pi over 2. So that's why this ends up being your only solution here. Okay. Now example E actually demonstrates the reason why I don't want you just to memorize this shortcut here, because even though we have the exact same notation, this is the inverse sine of the sine of 5 pi over 3, this does not just equal 5 pi over 3. And you can clearly see that that doesn't fall between negative pi over 2 to pi over 2, so that clearly can't be the output here for this inverse sine function. Now you can evaluate the sine of 5 pi over 3, right, which is what we did over here, and then go ahead and evaluate that ratio. So you'll get a ratio from this, and then you'll find the angle measure that corresponds to that ratio. But instead, let's just think about where 5 pi over 3 is. Okay, so let's say we have an angle. That angle ends up being here, down here. And then that's why on the unit circle, you measure that around and you end up with 5 pi over 3. Okay. Now, the idea of coterminal angles here is very important, and I think I just did a problem very similar to this already, but that measure here is the same if I want to go from negative pi over 2 to pi over 2, that specific range of numbers here, that's the same as the measure negative pi over 3. Okay, so this ends up being negative pi over 3. So to make a long story even longer, basically since 5 pi over 3 does not fall in the range of the inverse sine function here, we need to find a value, an angle measure that does. So it ends up being negative pi over 3 with the same coterminal angle as 5/3 pi. Okay, so let's move on now to the next question here, which I think you should be able to do already. But I just want to review real quick with you guys. Remember how up here we didn't have a value that was defined? So this, no matter what we do, is an undefined value. So we can't take the sine of an undefined value. Therefore, this whole thing is undefined. So kind of fun. That was a quick one. All right, let's move on to cosines, inverse cosines. Okay, now clearly the cosine function here, which is graphed here in black, is definitely not one-to-one either. We intersect many different times here with that horizontal line. So we restrict our cosine function also, but this time we restrict it between 0 and pi. Okay, And I didn't mention this already with the sine function, but this is a totally arbitrary restriction. It's just what we commonly restrict it to. You could restrict it anywhere you really want because you just need to make it 1 to 1. So if I wanted to, I could restrict it from negative pi over here to 0, or even from pi to 2 pi here, right? And I would still get a 1 to 1 function. It's just that we, in math dorkland here, we just use this common restricted domain from 0 to pi, okay? All right, so now our cosine function here, so this little box represents the cosine function. Our domain is now 0 to pi, and our range is still negative 1 to 1, but now that helps us to graph here our inverse sine function. So here we've got two different notations, inverse sine function, similar to that cosine function, and then the arc sine, or arc cosine, sorry, of x. Excuse me. All right, so I would like you guys to actually pause and try to graph this one here on your own, just using the same technique that we just worked on with the sine function. All right, so here's the graph of your cosine function here in blue and your inverse cosine function in red. So again, when you want to reflect something over the line y equals x to create that inverse, you're just going to take your coordinates and switch them. All right, so that's what I did here. It's not beautiful, but it's pretty close. It looks almost like it was a mirror reflection. Okay, so let's talk about the domain and the range now of your inverse cosine graph. So the domain here is from negative 1 to 1. So again, it just switches. And our range is from 0 to pi. All right, wonderful. Now we're going to use that idea again. When you're answering an inverse cosine, you're trying to evaluate an inverse cosine function, your possible answers come from this range here of values, okay, from 0 to pi. So everything here should be an output of 0 to pi as long as we're using an inverse cosine function. All right, when we complete the first question here to evaluate the arc cosine of 1/2, I want to keep in mind that the possible outputs for this inverse cosine only come from 0 to pi on my unit circle, right? That quadrants 1 and 2 basically. So right away when I see that it's a positive 1/2, I eliminate quadrant 2. There's no possible answers over here because all the cosines here are negative. So I definitely am going to get a value inside here. Also, it's 1/2, so it's the short value for the cosine, which means it's your high point for the sine. But anyhow, that is your pi over 3 family. So the arc cosine of 1/2 is pi over 3. Again, it's an angle measure, or an angle, it's an arc, really, measure. All right, now B is a little bit tricky. The reason it's tricky is that you see this pi here, and you think, oh yeah, that's right, the inverse cosine, it's defined between 0 and pi. But that's not actually true. It's defined, its domain is defined between negative 1 to 1, right? Its output, its range, is between 0 and pi. So this is a very deceiving question because this pi value is your input for the cosine, the inverse cosine function, which means it doesn't actually fall between negative 1 to 1. It's outside of that range, which means that this is actually undefined. This is not possible to answer this with a real number. All right, next up is problem C. Now in problem C, I'm going to evaluate the sine of pi over 3 first. So if I evaluate the sine of pi over 3, I end up with root 3 over 2. So now I look at the inverse cosine or arc cosine of root 3 over 2. Now the arc sine of root 3 over 2, that should produce an angle measure, right? And in this case, that corresponds to pi over 6. So at pi over 6, I end up with a cosine of root 3 over 2. Okay, let's have you guys do D, E, and F all on your own and then check with the key. All right, last up we have our inverse tangent function. So again, this is not a one-to-one function, obviously, but we restrict it within a specific domain here. Again, us math nerds get together and we say, let's restrict it between negative pi over 2 and pi over 2. So I have a domain now of negative pi over 2 to pi over 2 for my tangent function, which means my range doesn't get affected actually at all. It's still going to stay all reals. Okay. Now, when I go and restrict that function, now it creates a unique inverse function, which we call the inverse tangent function, which we similarly define as the inverse tangent of x or the arctan of x. Okay, either of those two work in terms of notation. So you'll see both interchangeably through your textbook and in your tests and quizzes. Okay, now let's go ahead and graph the inverse tangent function here, which I find kind of fun because in this case it's not bounded now in your domain. So it changes. Let's do our domain first. Our domain here becomes all reals. Our range is from negative pi over 2 to pi over 2. So this one's fun for some reason for me to graph, but it looks like this. Woo! And here's where you have two vertical or horizontal asymptotes. Alright, so that's our graph. Our asymptotes here look a little pathetic, but you've got one at y equals pi over 2 and one at y equals negative pi over 2. So remember that when you are evaluating any inverse tangent function, those angle measures that you get as outputs should always fall between negative pi over 2 and pi over 2. So first and fourth quadrant, if it's in the fourth quadrant, make sure you're using values that are negative, so like negative pi over 6, negative pi over 3, etc. So let's finish off the lesson here, evaluating a few inverse tangents. So we've got the inverse tangent of 1. Now the only time, if you're thinking in reference to just those values that we want, right, in the first or fourth quadrant, the tangent function is going to be positive 1 in just the first quadrant, so we're not going to use the fourth at all. So the tangent function is equal to 1 at pi over 4, because that's where you have the ratio root 2 over 2 over root 2 over 2, which is why you get 1. So this is pi over 4. Now for the arctan of negative root 3 over 3, this time you're definitely in the fourth quadrant. And this value is really like negative 1 over root 3. Some of you guys are more comfortable with this. This is just that same expression, just, rationalized. But anyhow, this value is going to have your x being root 3 over 2, and your y value is 1/2. So that coordinate is the long for your x, the short for the y. That's super close to that x-axis, which makes that a pi over 6 family. So that's value here is negative pi over 6. All right. Let's see. Now I'm going to skip to D, and then I'm going to actually cross off F completely. If I change the problem on your note sheet, I'd like you to try that problem. I haven't figured out if I'm going to change it or not. But if I did, go ahead and work out that problem, and then check with the key. Do the same for C and E as well. Alright, now on this question, I want to evaluate first the inverse tangent of root 3. So the inverse tangent of root 3 is definitely going to be in the first quadrant because it's positive. So I'm looking for a ratio where I have root 3 over 2 over 1/2, which means my y value is root 3 over 2 and my x value is 1/2. So that happens, let's see, that's the short long, which means that's the high point here. So again, short, long. And that would make that a pi over 3 family. So that's the pi over 3 value there. So the inverse tangent of root 3 is pi over 3. And then I'm going to take the cosecant of pi over 3. So I know I just erased that coordinate. It was 1/2 root 3 over 2, but the cosecant is just 1 over y. So we end up with 1 over root 3 over 2. So let's definitely make sure we rationalize this value here. So I'm going to multiply by root 3 over root 3. So I get 2 root 3 over 3. Alright, that's the end of the lesson. Nice job. I'll see you guys in class tomorrow.